All right, I'm gonna go ahead and just kick this off a minute early because I really want to make some more progress with this today. So, welcome back, guys. This is the second live stream of the day, third stream in the series of us building our engine based around Vulkan. And when we left off before, we were right up to the point where we created our swap chain. And I did have an issue that I said that I wanted to take a look at and fix off camera. And that issue was about the Q family indices. So I'm actually just going to show the diff here of the fix that I just put in for that. Basically, the issue is if the graphics Q index and the presentation Q index are the same, then Vulkan complains about it because it says, hey, you're trying to create the same Q twice. So really the fix was I shouldn't be doing that. And so what I did is I just did a quick equality check to say, hey, are they the same? And then only if they're not the same, I will add it to this indices, which is now a vector instead of a hard-coded array. The other change that I made, obviously, was to the loop, handle that. And obviously down here to point this to data and size appropriately. And with those changes, we're now in a good spot. We don't have any more validation errors or anything like that. So all that code is pushed to the GitHub repo, so you guys can go ahead and grab that. Cool. I'm going to go ahead and move on. So the next thing that we needed to do in our renderer is we obviously need to create the swap chain. And so we have a couple of methods in here querying swap chain support and so forth. However, we haven't actually gotten to the point where that creation has happened. So before I jump into that, I just want to mention that you know what? Actually, I'm gonna wait on that. I'll come back to that. So I'm gonna start by creating a new method called create swap chain. And this guy's gonna go at the bottom here. And in the constructor, I am going to go ahead and call create swap chain here. Okay, so the first thing I need to do is I need to get the Vulkan swap chain support details. So swap chain support, and again we're just going to use our query swap chain support passing our physical device. I also need to grab the capabilities. What I'm going to do is I'm just going to save this off as a slightly shorter variable just to make our code a little bit more concise. And the reason for that is, you know, typing swap chain support .capabilities is pretty long, so I'm just going to save that off. Oops. All right. So the first thing that I'm going to need to do is choose a swap surface format. So I'll loop through the formats that I have available, and I am you know what? I think I can just use the auto keyword for this one and loop through it the shorthand way. So I think I'm gonna go ahead and do that. So format in swap chain support.formats. Then we'll say if Swapchain support, oops, actually format. Okay, so give me just a second to find this here. Okay, so if the format is equal to VK format B8, G8, R8, A8, unorm, then that is going to be the format that we want to use. But we also need to check the color space of that format. So if we look at the color space and it is, I believe it was a color space. Was it sRGB? Nonlinear KHR. There it is. Some of those are kind of hard to remember because they're really long names. So in other words, these are our sort of preferred formats. So if we find one that actually has our preferred formats, then we want to use that one. So I'll say image format equals format. And I actually need to create this Swapchain image format. So go here. I need VK Swapchain surface. Oh, what's that again? What type was that? VK surface format KHR. Sorry about that. VK surface format KHR. And that's going to be Swapchain format. Okay, so we'll save that one off. I apparently can't spell either today. Swapchain image format. Okay, there we go. Now they match. And of course, we need to break out of the loop if we have found something that is ideal for us to use. If we get to a situation where we've gone all the way through this loop and the format is not ideal, then we would need to set it to the first one. So I think what I'm going to do is actually keep track of whether we found one or not. So I'll say found equals true, and then if not found, then we'll set the Swapchain image format to the first one. That way we at least have a fallback in the worst case scenario. The next thing is we need to choose a presentation mode. So that's going to be a VK present mode KHR. And again, we'll need to actually loop through. So I'm actually going to copy this loop here and just change this to presentation modes. Change this to present mode. And now we can say if preferred mode is available, use it. So our preferred in this case is going to be VK present mode mailbox KHR. That is going to be the ideal presentation mode. So if we look up in the spec, it defines for us what some of these presentation modes are. Let's see, that was... Here we go. We have all these present modes available to us. A lot of these aren't actually supported yet, at least not across the board. But this one specifies that the engine waits for the next vertical blinking period to update the current image. So it's basically used as almost as a form of VSync, kind of. It's used to prevent any sort of tearing on the screen. And so that's kind of the ideal one that we want to use. There is also a default one that we can use, which is this FIFO KHR. This is the only one that the spec actually mandates be always available on all platforms. So that's actually the one that we're going to fall back to. Anyway, so back in here, we'll set present mode. And we'll set that to, I just realized I duplicated this variable name here. Let me call this mode instead. So present mode equals mode. Okay, and then we'll say found equals true. Actually, so let me remove that declaration before it complains about that. And then one more time, we'll check if not found. Then we'll set present mode equal to first in, first out KHR. So that way we have a nice fallback available in the event that we have a implementation that does not support mailbox. Okay, so the next thing that we're going to need to do is we need to choose a swap chain extent. So what this basically means is it's the size of the swap chain images that are going to be used, and this is only going to be valid in the case that the window doesn't get resized. If the window gets resized, then all of this will actually have to be recreated. I'm going to tackle that definitely in a future stream, but for now, I'm just going to get the size of the window as it stands and use that as the swap chain extent. So if capabilities.current extent.width is not equal to U32 max, which I actually haven't defined yet. I'll come back to that in a second. Then we need to set a swap chain extent equal to capabilities dot current extent. Okay, so a couple of things. U32 max, basically what's going to happen is if it's set to U32 max, then it means that there is no defined width for this, which apparently is a possible thing. I've not seen it actually happen yet, but yeah, apparently that's a thing. So we have to account for it. In types, I'm actually going to add, actually, you know what? I'm going to add this into defines, not types. So I'll add that to the top. All the way at the top, actually. So if not defined, U32 max, define u32max, and that is going to be defined as, let me see if I can get this right, 0x 1 2 3 4 5 6 7 8 UI 32. End of. Okay, and what that's basically saying is it's defining just the shortcut for the maximum value that a U32 can hold. I'm going to go ahead and add. I'm going to go ahead and add one for 64-bit as well while I'm in here. So this one is just going to have 8 more Fs. And then that's going to be changed to a 64. Cool. So that should be all that we need there. Abilities that width. Do. Oh, did I? Put those semicolons again. Let's force a habit. Okay, so next thing we need to do is save off this Swapchain extent. So that is a VK extent 2D. So we need to save that off. All right. Now, we actually need one more change to our platform layer, and that will be to get the frame buffer size, because at least for right now, we have no way to actually tell what size that is. So thankfully, GLFW actually provides a utility for that, but that needs to be encapsulated in our platform class. So I'm going to go ahead and set that up now. But first, I actually need a type to actually hold that in. So I'm just going to create a quick struct. And I'm going to call it extent2D. And it's going to have a U32 width and a U32 height. And back here in our platform, we are already importing types. I'm actually going to add this right here, I think. And the reason I created a struct for this instead of using the Vulkan one is because it's a simple way to keep that abstracted. I still have to come back and fix this issue of having Vulkan types here later on, but this will be one less thing I have to fix down the road. So we'll call this get frame buffer extent, we'll say. And we'll implement this right before get required extensions. Okay, and then from there we'll need to create a extent2D extent and return it, and then of course call our method, which I believe is glfw get frame buffer size. There it is. We'll pass it window, and then a reference to the extents dot width and a reference to the extents dot height. And that's it. Or it should be there. Doesn't that take you? Oh, okay. I'm trying to use an unsigned type. I guess I'm going to have to... Maybe I should switch this to be signed. I guess that makes sense. because technically extents could be used for other things and they could technically be negative. So yeah, I guess that makes sense. Okay. So we have our get frame buffer extent. So back here we can actually use it. So extent 2D equals platform get frame buffer extent. Okay. And the next thing that we're going to need to do is obtain the or set rather the swap chain extent, and then make sure that it's clamped to a sane value. So we'll set the swap chain extent equal to, and we'll have to cast this to U32s in both cases. Vulkan extents expect unsigned. So U32 extent height. And we'll need to clamp this to an amount allowed by the GPU. And that can be obtained by using the capabilities. So we don't actually have a clamp method. So I think I'm actually going to kick off a little bit of a math library with some extensions, or some methods rather, utilities. I'm going to call this tmath. And I'm going to create a clamp method. That's going to be namespace regen. I don't know that I'm going to keep it in the namespace, but for now I will. Make a class called tmath. And for now, I'm just going to have a static U32, which means I need to include that. Include types. And it's going to be called clamp U32. I'm going to take a constant U32 value, constant U32 min, and const U32 max. And then I'll just implement it down here. So if value is less than min, we'll return min. Actually, if value is greater than max, return max, otherwise return value. Nice and simple, but we need it. All right, done with that. So now we can make sure that our extents are clamped. So first we'll do the width. So tmath, and I actually need to include that. Okay, clamp U32. We need swap chain extent dot width, and then we need to look at the capabilities dot min image extent dot width, and then for the max we want the capabilities dot max image extent dot width. And we need to actually do the exact same thing for height. I'm going to actually copy pasta that and change these all to height. Okay. So the next thing that we're going to need to do is we're going to need to create a couple of images to be used by our swap chain. And the number of images to be used is actually driven by the implementation. So we have a image, we'll call this image count, and it is determined by the capabilities.min image count. And then we're actually going to need one more than that. So trying to determine if I should, yeah, I guess we'll say if capabilities dot max image count is greater than 0, meaning that there is a maximum image count defined, and image count is greater than capabilities dot max image count, meaning we've exceeded the tolerable range, then we need to set our image count equal to capabilities dot max image count. So we're only going to basically double or triple buffer if the implementation allows us. If it does not, then we're obviously not going to do that. So this actually should have a +1. So typically, most of the time, your min image count is going to be 1. We want actually 2 images, so we just need to increment that one by 1. We could add more, but I don't think we're going to need more, at least not for a while. Eventually, that'll be hooked up to some sort of configuration, and then this will keep it from trying to create too many. So now we have the swap chain create info, and that is a VK swap chain create info KHR. There it is. Swap chain create info, and we'll initialize that with the S type being VK structure type swap chain create info KHR. So the first thing we're going to set is the surface equal to surface, the one that we've stored off. The min image count is actually going to be the image count. The image format is going to be the swap chain image format.format. The color space, image color space rather, is going to be the swap chain image format.color space. The image extent is going to be the extent that we just calculated. So swap chain extent. The image array layers is always going to be 1 unless we're doing stereoscopic 3D, in which case you may need more image layers, but I don't really want to get into that right now because we're not going to be doing that. So finally, we need to set the image usage to VK image usage color attachment bit. What that says is basically we're going to use this as a color attachment in the swap chain. Okay, so the next thing that we need to do is we need to set up the Q family indices. And in this case, this is where we're actually also going to use sharing of the Q family indices. So if the graphics family Q index is not equal to the presentation family Q index, then we're actually going to set up an array of these indices. So Q family indices, and that's going to be equal to, cast these both to U32, graphics family Q index first, presentation Q family index second. And then we have our swap chain create info image sharing, wait, is it image sharing mode? And we need to tell Vulkan that we want the sharing to be concurrent between. So we use VK sharing mode concurrent. Next is we need to set the index count. In this case, it's going to be 2. Why is this bleating? Oh, I forgot to make this an array. Okay. And then finally, we need PQ family indices, and we'll just pass it the array, which is Q family indices. Okay. Otherwise, if they are the same, if they're not the same, then they're going to run concurrently. If they are the same, then they're going to run exclusively. So in this case, we need image sharing mode be set to VK sharing mode exclusive. Okay, and the Q family indices, whoops, Q family count, index count rather, is going to be 0. And the Q family indices is going to be, oops, a null pointer. Okay. The next thing we need to set the pre-transform to capabilities dot current transform. And what this basically is it's basically telling Vulkan to not transform the image in any way before it draws it to the screen. It's just saying use it as is. And then composite alpha is going to be set to VK composite alpha take bit KHR. And this is basically saying that we want to ignore the alpha channel, that we're not going to worry about rendering alpha. And since our window is opaque anyways, it doesn't really matter. So the present mode is going to be set to the present mode. So the clipped, in terms of clipping pixels that are obscured by, say, other windows or whatnot, we want to set that to VK true. And so that basically means that if we have our window in the middle of the screen and something's overlapping it, whatever pixels are under that window that is overlapping it will not be drawn, they'll be clipped out. So it's just a small optimization that we can make. And then old swap chain is going to be set to null pointer. And this will, whoops, not bool pointer, null pointer. So this is actually super important to bear in mind, because when we actually go to recreate the swap chain on a window resize, we'll actually need to pass this in. So it's definitely good to bear that in mind, because that's actually what will cause some of the destruction of the resources held by that, is to pass it in here. But since we don't have one, since this is the creation of the swap chain, we don't need to worry about that. And of course, now we actually have to create the swap chain. So as you may have guessed, we're going to call VK create Swapchain KHR. And we'll pass device the create Swapchain create info. No pointer for the allocator as always, and then of course the swap chain, which we haven't actually created yet. So before I do that, I'm going to wrap this in a VK check, since this returns a VK result. And in Vulkan Renderer, I'm going to store off a VK Swapchain KHR called Swapchain. Cool. So, let's see, what is this? Oh, I need to pass this by reference. There we go. Okay. And so now we've created our swap chain. So I'm just going to build this real quick. Run. And have no validation errors. So we are good to go. Let me on over to chat. All right. Yeah, stream number 3 already. It's kind of quick. Oh, hey, buddy, what's going on? I come in here and the first thing I see is auto. You know, and that's kind of why I hesitated a second, because I hate the auto keyword, honestly. I was just like, well, do I really want to loop through all the indices unnecessarily? And I'm like, well, I don't know. So I did it in that case. That's pretty much the only thing I ever use it for, is iterators for STD containers. Yeah. Yeah, my first auto. Yeah, actually, it is the first auto in here, and it's kind of bothering me, so I might actually go back and get rid of it. Is the VS autocomplete with machine learning available for C++ auto? Also, I find it quick. I don't know the answer to that question. Okay. Wow, there's a lot of comments here. I don't know if I'm gonna make it through them all. Yeah, absolutely. I mean, I use autocomplete for all this stuff. I can't type all that stuff out. It takes way too long. Lazy's write once, copy paste in a new project. So I've done that before. Copy paste, edit, screw it, rewrite. That should be a t-shirt, sir. That really should be a t-shirt. Okay. Why is it T-math? What's the T for? Travis. I don't know. I couldn't think of anything better. I suck at naming things sometimes. Cool. No wrapping lines when they exceed the visibility limit. Yeah, I know. I'm actually planning on doing a cleanup pass on this class once we get something writing to the screen, because it is bothering me, but I'm trying to get to the point as quickly as I can. So yeah, I'm not doing a cleanup pass yet. Yeah, this is part of it. I did zoom it in a little bit so guys can see it. Yeah, I'm not using it. I'm not using modules in this. I won't be using that. Async stuff maybe at some point. Yeah, there are a lot of Vulkan terms. So I mean, this is intended to be sort of a high level, well, not even high level description. It's sort of just showing you how I'm going about developing it and hoping that it will help some understanding of it. But I can't go in depth on everything and explain what everything is, because if I did that, I probably would have written like 30 lines of code max by now. So you're wondering if Vulkan is worth going for instead of learning OpenGL. I would say yes, it is worth it, because everything is going to go this direction in the future. I mean, we're already starting to see OpenGL be deprecated on some platforms. It's still going to be a thing for quite a while on the web in the form of WebGL, I think, but you know, OpenGL is not going anywhere anytime soon. But I would absolutely learn Vulkan, because I think this is the way that all APIs are going to go in the future. Okay. Yeah, Mac hates OpenGL. Absolutely. Yeah. Mac. Yeah, my sentiments exactly. All right, cool. So let's crack on, shall we? So we're at the create swap chain phase. The next thing we actually need to do is we need to create some swap chain images and swap chain image views. And what these are the actual images that we're going to be drawing to and presenting. So the way that Vulkan works is you have an image, and anytime you have an image, you also have an image view. And you access or write to the image through that view. You don't access the image correctly. So that's what we're going to set up now. So I'm going to create a new method. I'll call it create swap chain images and views. And that'll work for now. Like I said, I'm going to be cleaning a lot of this up later on. Okay. So let me just grab this guy. So this is actually going to be pretty straightforward, I think. It's going to follow our typical pattern of get account and then fill in some data. So we're going to have a U32 called swap chain image count. We'll initialize that to 0. And then we'll do a vk get swap. Vk swap. Really? Apparently typing is just an issue for me today. Vk swap chain. Is it get swap chain, I think. Get swap chain images khr. There it is. Okay, so we call vk get swap chain images khr, pass it the logical device, the swap chain, and a reference to the swap chain image count, and then null pointer for the data. And that will get us our count, and then we need to actually store a couple things more, because we are actually going to have to keep copies of these images and views. So I'm going to create a vector of vk, I believe it's images. Yeah, vk images. And I'll call this swap chain images. And then I'm also going to keep a vector of vk image views and call that swap chain image views. Cool. So now I can say both of those actually need to be resized, because they're going to be created with a capacity of 0. So swap chain images dot resize swap chain image count. just copy pasta that. Change this to image views. Okay, and then I'm just going to copy that one more time. And in this case, I'm just going to pass the swapchain images.data. So that gets filled in. And there are the swapchain images. Now, the views are created slightly differently. So we're just going to create as many views as we have images. And the way we do this is creating a VK image view create info. I'm just going to call this view info and initialize it with a S type of VK structure type image view create info. Okay, and view info needs to have a few things set. So we need the image, which is going to be swapchain images I. The view type, in this case it's going to be a 2D view. We need VK image view type 2D. Next we have the format, which is going to be the swapchain image format. Then we need to set the some of the sub resource range properties. So an aspect mask, which basically is telling us that this is the a color image. That's what it's going to be used for. So VK image aspect color bit. We will be eventually using the depth bit for this as well when we create a depth buffer. But since this is just a color buffer, we're setting it to color bit. So we also need the base MIP level. We need to set to 0 just to let Vulkan know that we're not MIP mapping this. Sub-resource range level count. So we only have one level. Base array layer is 0. So again, we don't have multiple layers on this, so we just want to use the first one. And layer count is 1. Okay, and then we VK create image view, asset device, the view info, null pointer for the allocator, and swapchain image views, the index. That should be, why is this thing? Oh, I need to pass it by reference. Keep forgetting that. Okay. So we'll wrap this whole thing in a VK check. And that is all there is to creating the images and image views. It's not that much code. It's actually pretty straightforward, believe it or not. So up here, after our create swapchain call, we create our swapchain images and views. Cool. So as I like to do every time I hit one of these points, I like to run things and make sure that we're not getting any validation errors, and we're not, so that's good. All right. Let me just check chat real quick. Web GPU. Yeah, something from 2015. I mean, yeah, especially integrated cards. I mean, if you had a desktop, you'd probably get away with it, but um, I mean, is it mainstream yet? I don't know that it is. I mean, I know a lot of the big engines are using it, but I don't know if I'd consider it as mainstream as OpenGL. Um, maybe it depends on what the classification is, I guess. Um, yeah. See, so this is kind of what I was thinking is it has an NVIDIA card in it, so you're getting away with it because of the drivers. But um, if you had like an Intel or something, good luck. Good excuse to get one indeed. Yeah, I mean, honestly, I'm gonna do a little bit of testing of this engine on a Surface, which does have an integrated GPU. So we'll see how that goes. I don't think I'm gonna live stream from the Surface though. That might be a little bit painful. Dual. All right, cool. Let's move on. So the next thing that we need to create is something called a Renderpass, which basically bundles up a whole bunch of commands into one. And how do I explain this? It's it's a single run through of the rendering process. Um, so it's typically a lot of game engines, a lot of legacy gold game engines only have one where you just render as is. And then you may have additional render passes to do like full screen effects, things of that nature. Um, and you may have additional render passes if you have like multiple cameras or render texture, things like that. You may wind up using multiple render passes for that. But in this case, we're just going to have one. And if we need to extend it beyond that, we shall do so in a later video. So obviously we need to create a render pass. And actually just going to go call this here. And then go to the bottom. Okay. So the render pass is kind of another it's kind of another big section. There's really only two large sections to kind of go through still. There's the render pass, and then there's the pipeline that comes afterwards. I actually think the render pass might be a little worse than the pipeline. I don't know. We'll see. So the render pass basically requires us to set up a bunch of stuff before we actually start, or before we actually create the render pass itself. So the first thing we need is to create our attachments and our attachment descriptions, references rather. So we need one attachment for color, and then we also need an attachment for a depth buffer, which I've noticed that a lot of tutorials will sort of skip over the depth buffer and come back to it later. This is one of those things where I think it's just better to get it done and out of the way ahead of time, so that way by the time you render something, you don't have to worry about that. So we're actually going to take a couple of extra steps and make sure that that's created first. So first we have our color attachment, and we need a VK attachment description for that. I'll call this color attachment. And this color attachment just needs a series of properties set. I'm not going to go through necessarily all of these in great detail because it will take quite a while to explain. And some of them I've already kind of explained a little bit before. So obviously the format is going to be the swapchain image format.format. We've seen that a few times already. The samples is basically going to tell us that we're only going to use one sample, so we need vk sample count 1 bit. It's not 100% clear to me why they chose to set it up this way. That's a little bit strange, but that's the way it is. So we need a load operation, which is vk attachment load op. Let's see, that's load op clear, I believe. Yeah. So whenever we actually use this, we are basically saying that whenever we load it, we want to completely clear it, wipe it out. And then we have a store op, which is a vk wow, I can't type. Attachment store op, and then in this case we're going to call store, and this basically indicates that the results of this operation will be stored in memory so that we can actually use them later. And then stencil load op, which is for the stencil buffer. We're not going to load that, so we're just going to say vk attachment. Did I spell it wrong again? Attachment stencil op. Whoops, sorry, load op. Don't care. There we go. Okay, so next we have color attachment stencil store op, and that is going to be basically the same thing, except it's going to be a store operation. So I'm actually just going to change that. Okay, because we're not using the stencil buffer. We might at a later point, but I don't really see the need for now. So the initial layout is going to be undefined. So vk image layout undefined. And basically what this means is that the image that we use does not have to be in any specific format in order to be used when we start using it. So we don't have to transition it. So basically if we're saying undefined, we're saying we don't care. And then final layout is going to be vk image layout present source KHR, I believe. Yeah. And this is basically saying that it needs to be changed to a layout that is suitable for presentation. Now we need a color attachment. Oops. Reference. So this is a vk attachment reference. We'll call this color attachment reference. And we only actually need to set a couple of things on this. The first is going to be the attachment, which is basically an attachment index. So this is the first attachment, so it's going to be index 0. And then layout is going to be vk image layout color attachment optimal. And that's basically saying just use the optimal layout for this particular attachment. Okay, so next we're actually going to have to find the format that we want to use for the depth attachment because we don't have it. We had the swapchain format for the color attachment, but we haven't got one for the depth. So our depth attachment, we're going to find depth format. And to do this, we're basically going to provide a couple of candidates, and then we're going to loop through our physical device properties and find out which of those properties which of those candidates rather has the properties that we're looking for, and then we'll use that one. So in this case, I'm just going to use an array. So const u64 candidate count, and this is going to equal 3 because we only have 3 actually available to us. And then we're going to create a VK format called candidates, and it's going to be a candidate count. Right, and formats we're going to want to use is VK format D32 sfloat, VK format D32 sfloat, sfloat S8 went. That one. Okay. They all kind of look the same. Okay. VK format. And if those don't, if neither of those are acceptable, or found rather, then we're going to use D24 unorm S8 uint. So these are the 3 that we're going to choose from. There are, I think that might be, so there are a couple of other ones available, but I don't believe that they're actually commonly supported. So really we're just using these bottom 3 right here. These 16-bit ones I'm not going to bother supporting. We want a little bit more precision in our depth format than that. Okay, so next is VK format depth format, and we're going to iterate the candidates. So all right, buddy. The car alarm going off outside, and my dog is not happy about it. Okay. So that should be called candidates, not candidate. Actually, right. So I is less than candidate count plus I. Okay. So what we're going to have to do is we're going to have to actually get the format properties of each one of these formats. So to do that, we'll create a VK format property struct that we will store the data into, and then we'll actually query that. So we'll call VK get physical device format properties. Yeah. Pass it physical device, and the candidates index, and then pass in properties. Okay. And then once we have that, we can actually check for what flags we want. So to make this a little easier, I'm actually going to store a variable called flags. And in this case, we're only looking for one particular flag. So it's called VK format feature depth stencil attachment bit. And actually, I don't want to create this on every iteration, so I'm actually going to move this up there. Okay, and now we can say if properties and linear tiling features has the flag set that we're looking for, which means I actually need to wrap this in parentheses. So if that is set, then our depth format can be set to it. So we can say depth format as candidates I. Okay, and we can break. We also want to look at the optimal tiling features. So again, this is pretty specific stuff. I don't know that I necessarily want to explain all the ins and outs of this. I would suggest this is probably a place where reading about depth maps and the spec is a good idea. But basically, we're going to use this same logic here, where if it's found in the optimal tiling features instead of linear, then we'll use it as well. So this sort of gives priority to linear tiling features over optimal tiling features. And tiling features being how it's actually rendered. Okay, so I'm gonna, you know what, I really don't want to assume that we found something, because we could technically reach the end of this loop and not have gotten a format. So I'm actually going to also store a Boolean that gets updated. And then if we get here, for some reason we don't have a supported depth format, then we need to basically crash the application. Supported depth format. I don't think that would ever actually happen, but it's better to be safe than sorry. We don't want to silently fail on this. That would be potentially really bad and hard to troubleshoot. So, okay, so all of this to get to basically the same as what we have up here for our color attachment and our color attachment reference. And actually, these two things are so similar that for the depth attachment, I'm actually going to copy this and paste it down here. And I'm just going to rename this. I can type. Okay, and same with this. Okay. Now we are going to have to change some of these. So obviously the format is going to change to our depth format that we just got. We only want one sample, so that's not going to change. We still want to clear. We still want to store. Actually, no, we don't want to store that. Let's change it to don't care, because I don't think we actually. That doesn't actually matter. We don't need to store it. It can be thrown out as soon as we're done with that. The stencil load and store are the same. The image layout is undefined, but instead of presenting, we actually need to change this so that its final layout is suitable for a depth stencil attachment. So vk image layout depth stencil attachment optimal. Okay, and then the only thing we need to change here is our actually we need to change both things. So the attachment now is index 1, and the image layout is, instead of going to be color attachment, it's going to be depth stencil attachment. And that should be it for the depth attachment reference. Okay. So, before I continue, let me just double check chat again. Boy. Okay. There's a lot here. Dude, there's a hurricane over your city right now? That is crazy. Be safe, man. That's nuts. Let's see. Yeah, I don't know if I'm going to be able to actually start reading here. Yeah, exactly. Reasons for render passes, exactly. Vulkan doesn't really do anything automatically. Yeah, I would definitely follow this. You definitely want to read the specs once or twice. I mean, I've written a few projects in Vulkan now, and I still don't remember most of it. There's a lot of information to take in there. So definitely the spec is going to be. I mean, tutorials are great, but you got to read through the spec and understand it. Okay. Anyway, yeah. So about this, the game engines industry, big ones do not use STD at all and make their own STD. That is absolutely true. And I find a big reason for that tends to be so that they have more control over memory allocation, and they can trace it better using their own tool sets. At least that's the reason I typically do it. Yeah, I've read this too. It blows up. I mean, their types work just fine. And yes, this is actually a big issue too. It's one of the reasons. So I am using STD stuff in here right now, but I do actually have some drop-in libraries that I'm going to be putting in at some point that are going to replace a lot of these things, particularly vectors. Anything generic is crappy. Oh god, you guys are talking about ASM? Okay. I mean, yeah, I have challenged you to write some ASM stuff. You know, we'll see. Um, okay, yeah, Calvin, that's totally cool, man. I get it. Um, I'm gonna keep plugging away here and hopefully get something on the screen here sometime soon. All right. Speaking of which, let's finish up this render pass. So all render passes also have what's called a subpass, and it doesn't necessarily have to do anything different. in this case, all our subpass is going to do is basically just take in our attachments and use them. But you can have multiple subpasses, but from most of the reading I've done, there's not really a reason to. You really just need the one. So we're going to do VK subpass description. And the pipeline bind point is going to be, it could be several things, but we're actually going to bind it to the graphics pipeline. So pipeline bind point graphics. We're going to set a color attachment account of 1 because we only have 1. We'll set our color attachments to our color attachment reference. Whoops, got equals there. We're also going to attach our depth stencil attachment. So there's our attachment reference. So that's where all this stuff kind of ties into place and gets hooked up. Next, we need our Renderpass dependencies. So in this case, it's a VK subpass dependency. And we're just going to initialize that. So the source of the subpass is going to be external. And if we look that up, there's a few options for this. So in this case, I think if we're only using, yeah, that's what it was. Okay, so if we're only using one subpass, then we can just use subpass external. If we had multiples, then we would have to define what index that actually is. And then the all the rest of these things are basically bit masks for source and destination of different different parts of the pipeline. So our destination subpass is going to be 0 because we only have 1. Our source stage mask is VK pipeline stage color attachment output bit. Our dependency dot source access mask, not destination, is going to be 0. So we're not defining that. Next, our destination stage mask is actually going to be this same thing. So again, our destination is going to be to the color output. And then the destination access mask is going to be VK access color attachment read bit. And we're also going to want the write bit. So actually, I'm just going to copy that and OR it together and just do that. Okay. So the next thing we need to do is create an array of attachment descriptions. And this will actually be where we hook it up and everything else to our render pass. So we need a const u32 call this attachment count. I'm only going to have 2 of them since we only have 2 attachments. This should probably be handled in a more extendable way, but for right now, I'm just going to hard code it. So we have our array of VK attachment descriptions. I'm just going to call this attachments, and it's going to be of size attachment count. And we'll set that equal to, the color attachment will be the first. The depth attachment will be the second. And now we create our render pass. So all of that finally to well, create our create info and then create our render pass. So VK render pass create info, and this is render pass create info. And of course we need a S type, so structure type render pass create info. And the attachment count is going to be attachment count. The attachment, P attachments rather, or the pointer to attachments is just going to be attachments. The subpass count is going to be 1. Our P subpasses, oops. Our P subpasses is basically just going to take in our subpass. Got the equals again. And our dependency count is going to be 1. That is for this guy here. And our dependency itself, or P dependency array, is just going to be a reference to dependency. And now we can call VK create render pass, pass at the device, a reference to the render pass create info, null pointer for our allocator as always, and then we output to our render pass, which actually we haven't created yet. So before I go do that, I'm going to surround this in a VK check, and then in the renderer, all the way at the bottom, VK render pass, render pass. And we should be good to go. Need to pass this by reference. Okay. All right, cool. So that is our render pass creation. I know there's a lot there. And unfortunately, the next section of the creation of this is going to be a little bit bigger, and that is the pipeline. So let me just do a quick check on the chat. Yeah, Vulkan is super tedious. There's lots of it that I like. I like the explicitness of it, but you know, it does take quite a while to step through it. However, everything that I've read on it basically says that once you get past you know, the initial parts of it, the amount of code that you have to write to add features is not that much. And I've kind of seen that to be true, but I've also not developed an engine from beginning to end using Vulkan just yet. So I guess I haven't really reaped the benefits of that. I'm still sort of stuck in that section of you know, lots of code everywhere. Okay, so the next thing that we'll need to do is create our graphics pipeline. So our graphics pipeline is basically what everything attaches to, and it is what it's essentially the glue that connects a lot of this stuff together. So I'm going to create graphics pipeline, and add this. Cool. So, so this is where we hook in things like the viewport, the scissor clipping. We actually set up the rasterizer here. We do, quite honestly, a lot here that kind of starts putting the pieces together. So the first thing we'll do, as I mentioned, is the viewport. So we need a VK viewport. And the X is going to be 0.0F. The Y is going to be casted to an F32. And that will be the swapchain extent.height. Now, before I continue with this, I should mention that many of you that are coming from OpenGL are going to find something a little bit different about Vulkan, in that it actually does not render from bottom to top on the y-axis like OpenGL does. It renders from top to bottom. But however, most people have, or I should say most of my experience has been revolving around OpenGL, so I'm kind of used to that configuration. I may switch it at some point to not do that, but I'm actually going to set up the viewport to be flipped, so that it looks a little bit more like what OpenGL would. It's perfectly acceptable to do this if you plan on adding OpenGL support, which I do. It'll make things consistent in that manner. So for at least for the short term, I'm going to add this flipping to the viewport in order to handle this. So let's see. So the width is going to be again casted to an F32, which is a 32-bit float if you guys don't remember. So this is going to take the swapchain extent and width. Oops, width. Said width and accepted height. And then the height is actually going to be negative F32 swapchain extent.height. And that is actually what's going to perform the flip. And then, of course, the Y position is going to make sure that it's offset so that when you actually perform the flip, it doesn't just render off screen. Viewport min depth is going to be 0.0. And viewport max depth is going to be 1.0. This is another difference between OpenGL and Vulkan, is OpenGL actually has a minimum depth of -1 and a max depth of 1. So that's everything on the z-axis, sort of going into the screen, if you will. Whereas this and DirectX, I believe, are both 0-based, so 0 to 1. So the next is going to be our scissor. So this is basically what is going to determine where we render on the screen, or how it gets clipped. So in this case, we just need a VK rep2d. We'll call this scissor. And the scissor.offset is going to be 0, 0. And the scissor dot extent is going to be swapchain extent dot width swapchain extent dot height. Okay, and next we're going to set up a viewport state, and this basically holds both the viewport and the scissor information. So we need to create a VK pipeline viewport state create info. We'll call this viewport state, and it'll be initialized with a VK structure type pipeline viewport state create info. Some of these are so long that the IntelliSense window isn't even large enough to actually hold it. Okay, so viewport state, the viewport count is 1. The array of viewports is simply going to be a reference to viewport, or the address of viewport rather. The scissor count is 1, and the scissors is again just the address of scissor. Okay, and next we actually need to create a rasterizer. So this is a type VK pipeline rasterization state create info. Rasterizer create info. And this is another one where we're going to say VK structure type pipeline rasterization state create info. Okay, so depth clamp enable, there it is going to be VK false because we don't want to clamp depth. Rasterizer discard disable. We don't want the rasterizer actually discarding stuff. We want to handle that. So I'm going to set that to false. Polygon mode. This is basically whether we're doing lines or points, or in this case VK polygon mode fill. You can see here that there are some other types available, but we're interested in polygons. The line width is going to be 1.0f. Vulkan does support different line widths if your polygon mode is line, but anything over 1, I believe, requires an extension. So cull mode, we're actually going to VK cull mode back bit, meaning we're going to cull back faces. So the front face is defined as VK front face counterclockwise, and this is a result of us flipping the viewport. If we had not flipped the viewport, then the winding of the vertices would result in a back face that was counterclockwise instead of clockwise. But since we flipped that, and we're also going to be flipping something in our matrix to match, we actually need to have this set to counterclockwise. Depth bias enable, we don't need that. Depth bias constant factor, since we're not using it, set it to 0. Depth bias clamp, we'll set to 0. Wow, 0.0f. And depth bias slope factor is also going to be 0.0f. We may come back and enable some of these things later, but I don't really necessarily want to get into that too much right now. So just kind of accept those at face value, and we will edit those later on when we need. Okay. Even if we're not using multi-sampling, we still actually need to create a multi-sample state. So, okay, pipeline multi-sample state create info. The sampling state, I'll call it multi-sampling create info. Okay, and this has got another one of those. VK structure type pipeline multi-sample state create info. Okay. So this just has a couple things. Sample shading enable. We want VK false. Because we're not going to be using it. Rasterization samples, we're going to use VK sampler, or sample count rather, 1 bit. Min sample shading as 1.0f. Sample mask we're not using. Now, you might think that the default on some of these things is null pointer, but it's actually not. So in a lot of these cases where you have pointers to things, you actually need to explicitly set them to null pointer, or you'll run into problems. Alpha to coverage enable, we're going to not use that either. And same with alpha to 1 enable. Alpha 1 enable. Okay, so again, multi-sampling is something that we'll likely turn on later, but for right now, we don't want to use it. So I'm just setting it to some of these default things, saying we're not going to use it. Okay. Next is depth and stencil testing. And this is one of the reasons that I wanted to go ahead and create the depth buffer stuff ahead of time, is because of this. So, we need a VK pipeline depth stencil state create info. We'll just call this depth stencil. And of course, it has a type, so VK structure type pipeline depth stencil create info. Depth stencil. Let's see. So logic. Whoops. No. I'm thinking of the color blend state. I think all we need to do is depth test enable VK true. So this is sort of the equivalent of GL enable depth testing. And then depth write enable, we want that set to VK true as well, so we can write to the depth buffer. Depth compare operation, we want to use VK compare op less. So that is the pretty standard depth compare operation that is used in a lot of places in most game engines. Depth bounds test enable, we're going to mark that as false, because we don't want that. And we also don't want stencil tests either. Okay, false. Okay. Let me just take a quick break and look at the comments here. You know, I've actually been I've actually been thinking about this. I think it'd be cool to do another collaboration, but I haven't lined any up. I haven't really talked to anybody about doing one. Maybe it's time for an updated one of the one that I did with Jonas. I'm not sure. I'll have to think about that some. That's a good call though. I haven't even thought about that in a while. Let's see. So do you need the scissor to actually clip out the viewport? That's the thing, is you don't actually have to have it, technically speaking, but Vulkan's API requires it. So in theory, it's the same thing. It's not really clipping anything, but you know, it's a very explicit API, so it's required. Okay. So, the next thing is we actually have to set up attachment blend states. And this basically is what allows us to determine how these different attachments are used for blending, specifically color. And we're actually going to use mostly default options, but we still have to explicitly declare them. And so what we're going to start with is a VK pipeline color blend attachment state. And we'll just initialize that to default where we can. And this one we only actually have to fill in a couple things. So we need the color right mask. And this one we actually have to pass RGB and A. So the components for that are defined in this enumeration, the color component flag bits. So we're just going to OR those together. In A. God, I hate how long that line of code is. Okay. And then the next thing, actually I'm going to put this here since that line wraps, is blend enable. And we actually don't want blending, at least for right now. We will in the future when we start handling various transparencies and multiple passes and things of that nature, but for now we'll leave it off. Okay. So the next thing we need is a VK pipeline color blend state create info. Color blend state create info. And we will, of course, have a VK structure type pipeline color blend state create info. All right, so for this one, the logic op enable is false, or VK false rather. The logic op is going to be a copy, so in this case, VK logic op copy. And that's basically saying that we're just going to copy over the values. Attachment count is going to be 1 because we're only using the color attachment for this guy. So P attachments is going to be the color blend attachment state. And then we have the blend constants. and this is basically for RGB and A. And so in this case, first one is set to 0.0f, and so are the rest. So I'm actually just going to copy this and change this to 1, 2, and 3. Okay, so another thing I want to point out is anytime any of this stuff in here has to change, as the engine is running, you actually have to recreate the pipeline. So you really need to be aware up front of what you're going to use, what you're not going to use, before you create the pipeline. Otherwise, you're going to have to recreate it. And I mean, there's instances where you're going to have to recreate it anyways. But I just wanted to bring that up. So the reason I bring that up is because we have something called dynamic state. And dynamic state indicates things that can be changed without having to recreate this. So vk dynamic state, dynamic states, and that is an array, and it has two things that we're going to put in here. So vk dynamic state viewport. So if the viewport changes, we can accept that, and then vk dynamic state line width if we want to change that. I'm not going to be changing that right away, but I'll add it anyways, just because once we actually get a editor, we'll want to have the ability to do that. Okay, so obviously we're going to need a dynamic state create info. So vk pipeline dynamic state create info. I got that right? Yep. Dynamic state create info. And that, of course, is going to have vk structure type. Pipeline dynamic state create info. And thankfully this is pretty short struct, so the dynamic state count is 2, and the p dynamic states is dynamic states. That should have an s on the end of it. Cool. So that's all there is to that. Next, we need the vertex input info. So we basically need to determine what the binding point is going to be for the vertex info. So if you recall, in our shader, we had this location. This location is what this will be hooked up to. So to make this make a little bit more sense, we have a vk pipeline vertex input state create info. I'm just going to call this vertex input info. And of course, it's got one of those really long vk structure types. Type pipeline vertex input state create info. Okay, and the vertex input info has a vertex binding description count, which is basically saying how many binding descriptions do we have. Binding description is basically a bunch of data that tells Vulkan how that binding is supposed to work. And then we need to tell it the vertex attribute description count, which is how many attribute descriptions we have. And in both of these cases right now it's 0 because we're not actually passing anything in. When we go to actually create vertex buffers to load in data dynamically, instead of actually loading it in this way, then we're actually going to have to set this up. But for right now, I'm going to leave this as is. So the first step of that would be the describing what our input's going to be. The next is going to be the input assembly stage, where it takes the input and processes it and splits it into primitives that the next phase can then use. So in our case, it's going to be triangles. So we'll take vertices and turn that into triangles that then the next state can use. So we need a VK pipeline input assembly state create info. Input assembly. I'm just going to call it input assembly for now. VK structure type pipeline input assembly state create info. Okay, and now we just need to describe our input assembly process. So this is just going to take topology, which is, as we mentioned, we want triangles, so we want VK primitive topology triangle list. So this is basically saying one triangle from every 3 vertices, and we're not going to reuse them. And then our input assembly primitive restart enable equals VK false. And I'm not going to go into that right now. We will have to change that in the future, but for now I'm going to leave that as is. Okay, we're almost there with the pipeline, guys. We're almost there. This is the last major big hump that we have to get over, and everything else is sort of downhill from there to get something on the screen. So I'm going to crack on. Next thing is our pipeline layout. So we need a VK pipeline layout create info, and I'll call this pipeline layout create info, which of course has another one of these really long VK structure type pipeline layout create info. And so this is sort of where we connect all the pieces that we thus far. So our stage count, whoops. Actually, no. This is one step before that. We need to set our layout count to 0 because we don't actually have any layouts yet. When we have descriptor sets that that determine what our input layout will be, then we'll change that. Piece set layouts is null pointer because we don't have any layouts yet. Push constant ranges. Oops, that should actually be push constant range count equals 0. We're not using that. I messed that up. Push count. Yeah, okay, there we go. And then push count constant ranges is going to be null pointer because we're not using it. So we need to VK create pipeline layout, and this will take the device, the create info, null pointer for the allocator, and pipeline layout. And we haven't actually created that yet, so we'll need to do that. But before we do, wrap this in the VK check. This pipeline layout, and that is a type of VK pipeline layout. So VK pipeline layout, and I'm going to go ahead and create the VK pipeline as well, so that we don't have to come back here and do that. Okay, now is the pipeline create. So for this, we're going to need a VK graphics pipeline create info. We'll call this pipeline create info, and we'll initialize it with a VK structure type pipeline graphics pipeline create info. All right, so this is where we hook everything up. So we have our stage count, which is the number of shaders that we have. We use our shader stage count for that. Our P stages is going to be our shader stages data. Our vertex input state is going to be equal to our vertex input info. Our input assembly state is going to be equal to our input assembly. Our P viewport state is viewport state. Rasterization state is rasterization create info. Then multi-sample state is multi-sampling create info. Depth stencil state is depth stencil. And color blend state is going to be color blend attachment state. Or is it info? I think it's actually info. Yeah, great info. Okay. And then the dynamic info, or the dynamic state rather, is null pointer, because we will eventually be changing this to use dynamic state, but for right now we're actually not going to use it. So I know I created that object up there, but for right now we're going to set that to null pointer because we don't want to do that at the moment. So layout is equal to the pipeline layout. Renderpass gets hooked up now, so Renderpass. The subpass, and that's an index of a subpass, that is going to be 0. Base pipeline handle, we don't have one of those, so we're going to use a VK null handle. And our base pipeline index, since we don't have one, is going to be -1. Which is kind of weird that that sort of breaks the pattern that's kind of used everywhere else, where it would just be, I don't know why we have to specify it that way, but that's what the spec says. Okay, so next is VK create graphics pipelines, and the irony of this is that it can actually create more than one. Yeah, all of this, and we're actually just going to be creating one pipeline. So we pass device, or pipeline cache, which we actually don't have yet, and we don't need necessarily yet. We will need that in the future, but not for right now. Our create info count, there's just one of them. Our create info is we're just going to pass the address of pipeline create info. We are going to pass, of course, null pointer to the allocation callbacks because we don't have a custom allocator, and then store that off in pipeline. And of course, wrap that in VK check. Okay. Now, I think just for the sake of getting this far in the pipeline, I'm actually going to spit out a log saying graphics pipeline created, because we need a little bit of celebration for getting this far, I think. Let's build that and run it. Okay. And cool. So we have no errors or anything, so that's excellent. We actually got it in the first try. It's not too shabby. Cool. Let me check the comments. Yeah. You know, that wallpaper, I just found it on the interwebs, honestly. I don't even remember where I got it. I just liked it and downloaded it. Yeah, if I could find it, if I can find a link to it, I'll pass it to you. If not, I can always just DM it to you. Okay. 5:30. My time, at least. So the graphics pipeline has been created. There are still several more things we have to do, but that list is actually quickly dwindling. So we need to create a command pool. We need to create depth resources. We need to create our frame buffers. And we need to create our command buffers. And then we also need to create some synchronization objects. We need a couple of fences and a couple of semaphores. And then we can finally set up our render loop. We're already at another 2 hours. I don't know what heart. I don't know. Would you guys prefer that I push? Because realistically, I could probably push for another half an hour, maybe 45 minutes, and then I really do need to go. You guys just prefer I press on, or? Well, I'm not going to sleep yet. I should specify it's not 5 a.m., it's 5 p.m. But yeah, I kind of wanted to get to that point today, but yeah, we can wait for the fresh meat. Yeah, I guess I won't really rush it. I don't know, however, if I'm going to be able to stream next weekend. I hope that I will, but I don't know for sure, because I know I've got some stuff going on, so it may be a bit before I can actually stream again. Let me take a look at my calendar. So yeah, it may be, I don't know. We'll see it. It may be 2 weeks before I can actually do it again. But okay, yeah, I'm kind of tired at this point, so I think I'm gonna go ahead and cut this here, because, like I said, there's still several steps, and I think I'd rather come at it refreshed, as it were. So thanks for hanging out, guys. I know it's been a lot today. Yeah, it's been a lot. I'm kind of tired, so I really appreciate you guys hanging out. If you haven't already, feel free to subscribe and hop on the Discord server if you want to chat about it. I'm not always available to chat on there, but more often than not, I can respond. So cool. I'm gonna end it here. Thanks, guys. And thank you for that. Yeah, hopefully this is proving useful to some of you guys. And we will for sure have something on the screen next time because we don't have that far to go. I'm pretty sure I can handle that within about an hour. So thanks, guys, and I will see you next time.